as always, let me start with the introductions. So this course is Analog Wheelside Design. It's an NPTEL massive open online course. The instructor for this course is Dr. Iman Mandal. He is an assistant professor in the Department of Electrical Engineering at IIT Kanpur. Myself, I am the tutor. I hold these discussion sessions. My name is Mayank Kanpur. I am a PhD student in the Electrical Engineering Department at IIT Kanpur. So today we will be discussing whatever was covered in week 10 of the course. Okay, so in week 10 these are the key points, key summary points. Basically, you learnt about how to implement a VCVS. Okay, now that you have sufficient knowledge about what are circuits, okay, what are control sources, you have one type of control sources. Now you have sufficient knowledge about MOSFET implementation of those. So now you are expected to know how to build complicated circuits using those basic building blocks. So VCVS is such an example where you learn how to make this using the things that you have already learned. And in making this VCVS, we came across the need to have an amplifier which senses the difference, which works, which operates only on the difference, right? So from there the discussion evolved, and we learned about differential amplifiers. We also saw what is the differential and common mode response of this differential amplifier, and finally we also saw some more about we learned some more about differential amplifiers, mainly their Norton equivalent and everything, right? So first of all, is there any doubt in the content that was covered? So I have not looked at the discussion forum, so you can just tell me here if you have any doubt. If no, I will just proceed with the
mainly about swing limits actually in the various configurations. So you had given an explanation in the discussion forum, but still, if you can take a random circuit and just guide us how to get the swing limits, and suppose we want to generate different types of waveforms, like a pure sine wave or something like that. How do we do it without distortion? The usual thumb rule is that like VGS by 2, and you have got certain limits beyond which you don't apply those approximations, but still some insight into how to design sine wave generators and the gains for that in various configurations. Yeah.
So basically, the thing that you are asking me to do is it was already covered it was covered long back, right? The thing where you have to find swing limits of various circuits. So you just have to
Yeah.
go through, just have to apply conditions, okay, for linearity, and then you will be able to find the swing limits of any kind of circuit. So if you I cannot take it here, okay, right now. So
Okay.
because this was already
No,
covered long back.
what I wanted was just some sort of overall insight, just a 2 minute sort of some diagram,
Okay.
just
So
a
let's
sort of overview.
okay.
Yeah.
So I'm sure you know this, right? In the 2 minutes I
Yeah.
will only be able to do this as the
Yeah.
one that you already know. So this, let's say this is a
Yeah.
resistor here, okay, and
Mm.
this is VDD, and then you have a
Okay, take a common drain, for example, common drain or common gate, because yeah.
okay. So common drain. Let's take common drain only.
Yeah.
So let's take this as VDD, okay, and this is
Mm.
your this thing, and this is your, let's say, resistor here, and here you have applied certain voltage here, like this, like this,
Yeah.
right? So let's say
Yeah.
this voltage is in this manner.
Mm.
So this is some VCM and this is some
Mm.
VI. So
Mm.
this is some VI, and VI, let's say, is of the form VI is equal to some
Something sine,
A
VP
times
sine.
sine of omega naught t, right? If it is in this manner. Now you are told to find out what is the so in this condition you are, let's say you are asked what is the maximum value of A for which the transistor remains in saturation. Okay, so what will you do about it? So first of all, in this question you have to understand, whenever you are asked to find out what is the swing limit of something, the first thing that should strike your mind is that what causes the circuit to become not circuit to go out of saturation. Okay, the first thing that is this is the first thing that you should ask yourself, that okay, let me apply a signal here. So let's say this is biased in perfect saturation condition. Okay,
Yeah.
let's say this is
You could
biased.
please just draw the characteristics also, like the square. There's a quadratic characteristics and the VDS
I'm coming
V.
to that. Okay, so let me finish this first. So the thing is that, let's say this is biased in certain situation. Okay, let's say the
Yeah.
VGS is good right now. Okay, VGS is good,
Yeah.
and this VDS is also good. It's fine.
Correct.
This is the bias
Yeah.
condition. Let's say, so as
Yeah.
if you want to look at the this thing. So let's say this is your ID versus VGS, now.
Hmm.
So let's say in this graph, you know that this is, so it follows square law only in this region, right?
Linear saturation region. Yeah,
Right,
like that.
and
Yeah.
beyond that becomes slightly, so it is actually in this manner. Okay,
Yeah.
but
Yeah. Linear for the first few till the knee point, and yeah.
no. Its VGS is very less, then it basically follows a this thing. It goes into cutoff, we say, but it's not actually that exactly. It is actually sub threshold. Okay, something which you will come to know only later when you take higher level device courses. The behavior
Okay.
here in this region is exponential. Okay, so let's not
Yeah.
worry about that. We are not going to concentrate on that region. We are
Yeah.
going to concentrate on this region. Okay,
Okay.
to the right of this boundary. So here it is square law, fine, and let's say our device was biased somewhere in here. Okay,
Yeah.
that is here, this place. So this is, let's say, your VGS Q, and let's say this is IDQ. So this is IDQ, and this is VGSQ. Okay, so VDSQ will also, so VDSQ comes after that. Okay, so you will
Hmm.
this is the basically whatever drop will be here. Okay, there will be some drop here, right? So what will be VDSQ, by the way? This will be VDD minus, in this case, what will be VDSQ?
Uh, uh, VDD minus IER, like
Yes,
I
yes,
yeah,
yeah, it is that only.
IDQR. Yeah.
Yeah, it's fine. Good. So this is what it is. Now, now you have to ask the following question, that okay, now let me increase the bias. So bias remains constant, right? Now you have applied a
Hmm.
signal here, right? This signal is
Yeah.
sinusoidal. So sinusoidal signal is, what is a sinusoidal signal? If you try to visualize it here, so sinusoidal around this point, so
Yes.
net voltage that you will see here will be what? VGS plus this small
Hmm.
Vi, right?
Correct. Correct.
Correct.
Yeah.
Uh, Not even VGS. Sorry, the gate voltage here will be VG, that is VCM. Okay, VG will be VCM, right? So please notice that VGS is not equal to VCM, right? In this case, VGS is not equal to VCM.
Mayank,
Yeah,
sorry to disturb you.
yeah.
Uh, After how much time you will upload this video?
And I will upload today itself. So last video also I uploaded on that day itself.
Yeah, yeah. Just I am just asking. I have to leave.
It's fine. You can go. You don't have to
Sorry.
upload.
Thank
It's
you.
fine. Yeah. So as I was saying, this VGSQ is not equal to VCM, right? In this case, because the source node is not equal to 0, right? So in this case, this gate voltage here, VG, will be equal to
Hmm.
what? VG will be equal to VCM plus this VI. VI is what? 8 times sine of omega naught t. Now,
Yeah.
let's say our so basically my VG here, it is VCM plus minus something, right? It is always moving around
Hmm.
VCM. So
Yes.
let's say because of some reason this starts to go down, this node voltage, when Vi is taking its negative excursion. When the sinusoid is going below, right? Sinusoid has two phases, right? It is above
Hmm.
zero half the time, or below zero half the time. So
Okay.
let's say this goes above. Sorry, this goes below. Okay. Now this node voltage, if it is decreasing, right?
Hmm.
That is basically when I am in this region. So this is VCM, and my Vi is like this. Okay.
Hmm.
So I'm in this region. No, sorry, not this, but this region right now. So here this is the net voltage. Okay. This is the net total voltage. So let's say I am in this region. So what is going to happen because of that? When the VCM is going, I mean, when the gate voltage here is decreasing, what is going to happen?
And IR will also decrease.
Yeah. So basically, what is going to happen? IR, you are saying IR will decrease.
Yes.
IR will decrease, right?
Yeah.
And you are saying that because when the gate voltage is decreasing, it is expected that the source node voltage will also decrease, right?
Yeah.
And because of that IR is decreasing, and because of that, well, I'm sorry, because of that the current is decreasing, and IR is also decreasing, right? Something like that is happening.
Yes. Yes.
Something like that is going on. So
Yeah.
so one thing is sure, right? When this node voltage is decreasing, what is happening to this guy VDS? So drain is fixed, right? Drain is fixed here.
Yes.
Source is
Yes.
going down, so VDS is increasing, right? When this guy is going down, when VG is going down, this source voltage is also going down, but VDS is increasing, right?
Okay.
So
Yeah.
in that condition, do you think it will ever go out of saturation?
No, it won't go out of saturation.
It can go out of saturation into cutoff region, right? So that is a whole
Yeah.
different thing. But it will not
Okay.
go out of saturation into linear region, right? Because
Correct. Correct.
drain voltage is not, drain to source voltage is not decreasing, right?
Is always greater than the VGS minus VTH.
Yes, I mean in this
Yeah.
situation at least it is not going down. It
Yeah.
is already, it is only going, it is only becoming larger than what it was in the bias condition.
What is required
Yes.
for saturation?
Yes.
Yeah.
So now let's say it is in this region. Sorry.
Mm.
Let's say it is in this region now. Now the gate voltage is going up. So then what is going to happen?
Current goes up and IR increases.
So source
And
voltage also is going up, right?
yeah.
So when the source voltage goes up, what happens to the VDS?
Mm.
What happens to VDS?
It reduces.
It reduces, right? Whereas
Yeah.
if you closely look, I mean in any source common, this is a common drain configuration, right? So in common
Yeah.
drain configuration, the gate to source voltage remains almost same, okay? I mean it doesn't reduce a lot, okay? Because gate to source, the gain is almost equal to 1, right? In general, I mean it is less than,
Yeah.
slightly less than 1, but it's fine. I mean it doesn't matter much. But drain to source voltage will decrease, right? Gate to source voltage
Okay.
will also decrease, but it will not decrease that much as drain to source voltage. So what is going to happen here? There might be a possibility of this one going out of saturation into linear region, right?
Yeah.
So this is the first question that you need to ask yourself. So what happens when the when the sinusoid is going up or down? So this is the first question that you have to ask. So what are the conditions where the transistors can go out of saturation? Once you are able to pinpoint that condition, okay, once you are able to pinpoint that condition, just apply that condition in the equations. So the equation that you need to write here will be that at the border of saturation.
Okay, so the equations I can manage myself. I just wanted the process, right? Like, okay, so for whenever we see a new circuit, what we have to essentially look at is the input variation and the relationship between the DS and the VGS.
Yes.
And
exactly.
then we have to decide. We have to systematically decide it's going from saturation to linear or saturation to cutoff.
Yeah.
So depending on the configuration, like the conditions will be like, if it increases, it will we'll use that saturation to linear one, and in some circuits, when it increases, we'll use the saturation to cutoff one also.
Yes, exactly. Yes.
Yeah. Okay. That's all I wanted. Yeah. Now, this I think after this we can take forward, like it's yeah. And one last question. The professor remarked that like you can have a resistor also in the drain also, like between VDD and
you can have yes, you can
yeah,
have
even in this common drain, and take the output from the IR only, from the output from the source.
Yes.
So in that case, like why, like any insight into like all of the circuits in the problems, they are like they are directly connected to the VDD. But if I put a resistor there, what is the use of that? And like some comments on that, does it? I could not work out how it stabilizes or like helps with the whole thing.
There's nothing stabilizing kind of going on here. It just depends upon your application. Okay. So if you want something, so sometimes resistor is required to. So everything that you see in the circuit is to bias it, right? Bias and to achieve whatever you want. So if you see a
Okay.
resistor on the top of that in the drain, so it may be
Hmm.
because it needs to be biased properly or anything like that. Okay, maybe the
Okay.
drain to source voltage is too large, so that is not required. So maybe it is there to bias it. But in general, in common drain circuits, I have not seen resistors being used on the top. Okay.
Okay. Okay.
Yeah.
Yeah. Yeah. Thank you very much. Like, yeah, I've already taken too much time here.
It's fine. I
Thanks.
mean, you have
Yeah.
to ask the questions which you have.
Yeah.
Right? So the key takeaway, if I would if I summarize it, the key takeaway for
Hmm.
any swing related problem is that you first have to
Hmm.
identify the root cause
Hmm.
of basically the root which is causing the swing limit. Okay, what is happening as the signal at the input is changing? What is going to happen at
Okay.
various nodes? Once you identify that, it is very easy.
Hmm.
After that, you just have to apply the basic conditions, and you'll be able to find it out.
Correct.
Fine.
Yeah.
Good.
Uh,
So let's do.
Thanks.
Yeah. Welcome. So today the first question is very easy. I would like you to answer it as quickly as possible. So this you must have already seen earlier also. So tell me, this is the circuit, okay? R1 is 20 kilo ohm, R2 is 100 kilo ohms. This is an op amp, okay? It's so when I denote a circuit like this, what does it mean? A simple triangular box. What does it mean? It means it is a voltage controlled voltage source, okay?
Correct.
So it's a simple triangle, right? So it's a voltage controlled voltage source. Basically, it means that the so you have two nodes, right? Like this. Sorry, this is my this. Okay, and here you have a voltage source. This is ground, and this is some AB times V1 minus V2. This is V1, this is V2. Okay, this is what it means. Got it? Yeah. So now that you know that and know this, tell me, answer these questions. So what is going to be this? The answer to this, what is V naught if AB is equal AB tends to infinity? Yeah, I would like you to answer. I mean, I'm not I didn't, when I was framing this question, I didn't want to answer it myself. This should come as quickly as possible from you guys. So what is going to be V naught if AB tends to infinity? This is classic op amp problem. This becomes an ideal op amp, isn't it? So what is going to be the value V0?
So we just put the current equation on that and get the feedback and
Yeah.
equate
So
it. So
what
then,
will it be? I mean, you should solve. I mean, when you sit for this discussion session, you have a copy and pen, right? So start doing that and tell me
okay, let's
quickly. So what will it be?
AB times VI.
VO
AV times VI. So AV is infinity. So
AV
are you saying that V0 should be infinity?
VI minus VF is equal to AV into VI minus VO
All right.
into
So tell me, what will this node be? What will this
It is 6. 6.
6? 6 what?
2.
6 volts.
No, 6 volts. How can be 6 volts? This is, I'm asking, this is VI. I have not said anything about VI, so it should be 6 times VI, na?
V naught by VI equal to 6.
Yeah, V naught by VI is 6. So V naught is equal to 6 times VI. So those guys who didn't understand, so tell me, what will this node be equal to? This will be VI, right?
VI.
Virtual short, isn't it? This is infinite gain here, right? So okay, so let me solve this quickly. So the way to solve this would be, so let's say this is not VI, let's say this is VX. Okay, so what will be the V out in that case? V out will be Vi minus Vx into AV, right?
Yeah.
This is Vi, sorry, V0. And what is the relation between Vx and V0? There is a resistor divider here, right?
Yeah.
So Vx is equal to V0 times R1 divided by R1 plus R2, isn't it? So if you put both of these here, so what will this V0 be? Equal to Vi minus Vx is equal to V0 R1 divided by R1 plus R2, and this into A time AV. So what will this be? V0 plus, or rather common, 1 plus AV times R1 divided by R1 plus R2 is equal to AV times Vi. So this becomes,
Mayank, you said it is VCCS, right? Op amp is.
I said VCVS, right?
No, no, CS you have said, I guess.
I said it is VCVS. Whenever it is, I even made the symbol here, right? How can it be VCCS? Whenever we have a triangular box here, triangle like this shown here, it is a VCVS. Got it?
Okay, okay.
Yeah. So, but anyway, your answer was correct, I think. Yeah. So
Yeah. R1 plus R2 by R1.
So yeah, so tell me what will, so V0 is equal to, or V0 by Vi is equal to how much? It is equal to AV time AV divided by 1 plus AV times R2 by R1 plus R2. Correct? Now, so this is the expression, right? This is in general true for any AV. Correct? Now in this, if AV is equal to, if AV tends to infinity, what is going to happen? You take AV common, right? From both sides, from numerator and denominator. AV times 1, and from the denominator also, if you take it common, so this becomes AV times 1 over AV into, sorry, plus R2 over R1 plus R2. And if AV is tending to infinity, what is this guy going to become? This guy will become equal to 0. I mean, this 2 will cancel out. This guy will tend to 0, right? So in the, so ultimately this will tend to what? 1 over R2 divided by R1 plus R2, which is in other words is 1 plus R1 over R2. Correct? Is that correct? And what is R1 and R2? Oh, sorry, I didn't see it. Is this correct or wrong? I have made a mistake somewhere.
It's R2 by R1. Like.
I have made a mistake somewhere?
Yes. Yeah, yeah. It's R2 by R1. 1 plus R2 by 1.
I made a mistake here. No? I made a huge mistake here. It is 1 plus R1. Right? So mistake.
Yes.
That's by the, that was wrong. It is R2 by R1. Cool. So yeah, so this is the final thing. So how much will this become? R2 is equal to 100 kilo ohms, R1 is equal to 20. So 100 by 20 is 5 plus 1, 6, right? So I think our friend here was correct. It is 6 times Vi. Correct? Now tell me what is going to be V0 if AV is equal to 100 instead of infinity. So you just have to put it here, right? So tell me quickly, what will it be? If AV is equal to 100, what is going to be this value? What is going to be the value of this guy? V0 over Vi. Quickly. So it will be 100 divided by 1 plus 100 times how much? It is rather, it is not that interesting in this manner. So let's do some transformation here. So divide, so take divide by R1 by R1 plus R2 on top and bottom. So what will it be? Okay, so tell me what will it be. 100 divided by 1 plus 100 into, it is 20 divided by 120, correct? So this is 1 over 6. So what will it be? 100 divided by 106 into 6. How much will this be?
5.66 volts.
5.66
volts.
Again, who is saying it is volts? How can it be volts? This is unitless, right? V0 over Vi. There is no volt. It is
Yes.
unitless.
It's 5.66. 5.66 PI.
Correct? 5.66. Nothing. No.
Mayank, can you explain that above? How did you got those two equations once again?
This one. This two.
Like the first step and second step.
Yeah. So in the first step, I just assume this node voltage to be some Vx. Okay. You don't know, na, this node voltage. How will you solve? You just have to assume something here. I assumed that this node voltage is some Vx. Then I wrote the equation of op amp, this one VCVS, that if I know Vx and Vi, so Vi minus Vx into A bit becomes equal to V0, right? This is the first equation. Now I also have to somehow eliminate Vx, which I assumed, right? Because I have to find it out. I do not want to, I mean, I only know what is Vi, right? And I want to find out what is V0. So I need to eliminate it somehow. So what will I do? I wrote another equation to get Vx. So basically Vx is what? So you can see this resistor divider, right? It's a voltage here at this place, and Vx is basically some, it is a resistor divider ratio, right? That is going to appear.
Yes.
That's what I have
Yes.
written here. So this is 5.66, right? There's no doubt here. So you can see clearly that once the gain decreased, so you know that if the gain is infinity, you were expecting V0 to be 6 times Vi, right? You were expecting a signal amplification of 6 times, correct? That is what you were expecting here when the gain was infinity. However, when the gain became equal to 100, which is also not very less, it is quite good. If the gain is 100, it's quite good. However, you can see clearly that the signal amplification ratio got reduced to 5.66, right? Is that clear? So it clearly say, what I wanted you to take away from this exercise is that you can understand how critical this guy is, the gain of this guy is. This guy's gain should be really large for this op amp to behave as an ideal op amp. Okay. You also have learnt it in the in this week also, right? What is the state? What is the error? If the DC gain is not infinite, what is going to be the error? Steady state error. So that you have learnt. Anyway, we are going to attempt an exercise on that, but this is just to give you a flavor. Now tell me what is.
One thing, like the virtual ground concept, right? So professor had mentioned it even in one of the circuits classes, and like I could not grasp that concept very nicely. Like, in the sense, when can you say that there's a virtual ground between 2 points, and when is it that you cannot say that those two potentials are equal?
Okay, so there is a difference in virtual ground and virtual short. When op amps we have virtual short, okay, and so that is in ideal op amp we have virtual short. That is when if the ideal op amp, in the ideal op amp, what do we have? We have infinite gain, right? We have infinite gain. So whenever we have an infinite gain in an op amp and you connect it in negative feedback, then basically you expect the voltage at the input to become equal to 0. So if I want to explain it, 1 second. So let's take this basically. So this is a digression. Alright, so if you have an ideal op amp like this is not a good op amp. If you have an ideal op amp in this manner, so let's say this is V1, this is V2, this is V0. So let's say this is not an ideal op amp, this is some op amp with gain AV. Okay, so what is going to be V0? V0 is going to be V1 minus V2 times AV. Alright, now if this AV becomes infinite, okay, so in that condition also V0 is equal to what? Infinite times V1 minus V2, right? Is that clear? Now
Yeah.
it is not very good to write it in this manner. Actually it's a limiting thing. So V0 tends to V0 equals to AV into V1 minus V2, which actually tends to infinite times V1 minus V2, right? This is how it is. Now tell me, if V1 minus V2, this quantity, this guy, everything in the bracket, if it is anything which is not equal to 0, what is going to happen to V0?
It's going to go to infinity.
It is going to go to infinity. Very good. So we know that V1 minus V2, if it is anything but 0, this guy is going to become infinity. That is good. Now that you are clear on this, now let's try to do this. The same op amp we take, okay, and we put a negative feedback across it, okay. For time being, just assume it is like in this manner. It's in this manner, just a simple this thing. And so fine, this is how you connect negative feedback, right? You connect the output to the negative terminal of the negative input of the op amp. So this is a negative feedback. Fine.
Yeah.
Now tell me, you have applied an input here, okay? So the op amp knows nothing, but op amp can only process information that is applied at its input, okay? So but what you have given, you have only applied one input, the other input is connected to the shorted to the output, right? So how does op amp work in that manner? So let's say this voltage is some any voltage V2 again, okay? So again op amp only knows one equation for it, right? It has only been taught only one guiding principle for itself. What is that? If you are seeing any signal at the input, so it should be V0 should tend to infinity times V1 minus V2. That is the only thing that op amp knows, right?
Yeah.
In that condition, if so in that condition, tell me what in this situation, V2, if it is not equal to V1, what should be V out?
Infinity.
Right? But you can also see this is a contradiction, right? If V out is equal to infinity, so it is also connected directly to V2, right?
Yeah.
So if V1 is let's say, okay, not in this manner. So let's talk in this manner. Let's try to understand in this manner that if V1, let's say case 1, that V1 is slightly greater than V2, not slightly, but let's say V1 is greater than V2, okay? So what is going to happen? V0 will become infinity, right? V0 will go to plus infinity. So you can see that the moment V1 becomes equal greater than V2, if this guy is greater than V2, so what is going to happen to V0? It's going to blow up to infinity, right?
Yes.
So you can see that this is not possible because this is also connected to this guy, directly shorted. So moment and I assumed initially that V2 was less than V1, So V2 was less than V1. This is something which I assumed, but you can see that the moment V2 becomes less than V1, what is going to happen? The output is going to force V2 to become very large, right?
Yeah.
To 10 to infinity, it was tends to infinity.
Something which is not possible, right? So this means that our assumption is not right, isn't it?
Okay.
Huh? Now take the another case.
Okay.
Now take another case. So case 2, when V1 is less than V2. Let's assume that V2 is
Yeah.
slightly greater than V2. Now let's say if this happens, what is going to happen?
Minus infinity. Yeah.
Right?
It's going
Minus
to
infinity.
Minus infinity.
It is immediately going to go to minus infinity, which means that
Yeah.
again,
Hmm.
if V2 was becoming larger than V1,
Hmm.
this output
Hmm.
guy, it is going to force V2 to become low, right?
Yeah.
So which means this is how negative feedback principle works. Okay, in basically
Hmm.
what is happening is, in this condition the circuit is enforcing its
Hmm.
input to go close to V1. Are you able to
Hmm.
understand that? It is not
Yeah.
letting
Yeah.
it to we have taken two conditions, right? One where V1 was equal, one where V2 was less than V1, and one where V2 was greater than V1. In both situations we saw that the circuit
Hmm.
it behaves in this op amp, and the
Hmm.
connection like which is placed here, it is enforcing the this guy here to go
Hmm.
closer and closer to
Okay.
the input, right? V1,
Yeah.
isn't it? So and you can see that if it is infinite, if the gain is infinite, it is
Hmm.
very it makes sense that this V2 can be nothing but equal to V1, right? Because if it is
Yes.
anything but V1, what is going to happen? V0 has to go to either plus infinity or minus infinity, right? And that is
And the
not
negative feedback will force it back to its like equilibrium position.
right, exactly. It is going to enforce it, and that is only going to happen because it is connected in this manner. If this connection
Okay.
was not here, like in this
Hmm.
condition, anything can
Hmm.
happen. Okay, but
Hmm.
this connection is here. That is why V2 can only be equal to V1 and nothing else. So you can clearly see that even when we have not applied it, we have not placed any direct connection between these two guys, still
Okay.
these two
Hmm.
guys are always equal to each other, isn't it?
Oh.
Is it, Mayank?
Okay.
I think it will swing between plus infinity to minus infinity always.
No, it
It
will
will
not.
not be stable
Why are you saying that?
because your, let's say your V1 greater than V2, then it V0 will go to the plus infinity, right?
No, but that's not how it works. No, I mean, I said that things
So
are happening
how it will be
sequentially.
stable?
Things,
That
I
is
mean,
my
I am saying
question.
that things are. I'm explaining in this manner that things are happening sequentially, but that is not how it is going to happen. It is going to happen instantly. Okay, the moment it sees, the moment V1 you apply here, okay, everything happen in an instant, and this guy will be forced to be equal to V1.
Uh, so it is purely an abstract concept just for the sake of our convenience. What I was thinking was it was like because the op amp input impedance is infinity and no current flows between V2 and V1. So so it must be sort of equal to V1 and V2 must be, but I think that conception is wrong actually.
No. So what
So
I
it's
explained here is the one thing that you have to understand, that
okay.
op amp
Hmm.
basically because of negative feedback here,
Hmm.
the node V2, this voltage
Hmm.
V2, okay,
Hmm.
it is being
Hmm.
enforced to be equal to V1, okay, and even
Okay.
when we have not placed any direct connection between
Hmm.
this between these 2 points, still there
Hmm.
seems to be it seems
Hmm.
like there is a short, right?
Okay.
I mean, it,
Hmm.
it appears that there is a short even when we have not applied, when we have not put any direct connection here. Correct.
Okay.
So
Hmm.
this is how this is what it means when you say virtual short. So it is like it behaves like a short. It is not
Hmm.
actually shorted. Okay.
Okay. Okay.
This happens.
So in a more complicated circuit with many nodes like this, for example, like there are more complicated circuits with multiple feedback loops, and say like a V at 3 or 4 different points, the potentials are somehow equal. Can that also be considered as a like virtual short or virtual thing, or like that is a different case altogether? It's just applicable only to a 2 points which are very specifically related.
I mean,
Like
virtual short happens when points are which two node voltages which are always equal to each other. Okay, which is enforced by some kind of circuit mechanism. Then you can say it is a virtual short. It can also
okay,
happen that two node voltage are equal to each other in some condition. Okay, that cannot be
yeah,
called as virtual short because it may happen that in another condition that will become not that they might not be equal, right? But
Okay,
the thing is that
direct feedback relation is absolutely essential to call
no, no,
like
no.
2 points as virtual short.
I mean, some kind of information exchange has to be there, right? Only then will one node know where the other node is moving, right? Some kind of information exchange
Okay.
has to be there, and that is called
Okay.
feedback, right? That is
Yeah.
called feedback, information exchange, right? What is happening
Hmm.
here? What is feedback? Some information is being exchanged, right? Whatever is being
Yeah.
applied, and that information is being sent back to the input.
Hmm.
Feedback, right?
Okay. Okay.
Now,
Thanks. Like, yeah, I've got like. Thank you very much for the explanation.
yeah, fine. So they tell me. So what is R out in both these conditions? In both of the conditions where AV was infinity and where AV is equal to 100, what is the output resistance? Looking from this side, what is the output resistance looking from this side? What is going to be the output resistance looking from this side? So what is this? What is this op amp? It's a voltage controlled voltage source, right? It's a voltage controlled voltage source. So what is going to happen? What is the output resistance of a voltage controlled voltage source?
0. Like,
Yes, it is 0. So it doesn't matter, na? I mean, there is it doesn't matter even if you, so this is if you try to look at it, so this is the situation, that this is the equivalent circuit. So this is the same circuit. I just have, this is ground, this AB times AB, this is VI, let's say this is connected to some VI, so this is VI, and here you have R1, and between these two guys you have R2. And here I'm asking the question that what is the output resistance here. So you can clearly see that
It is parallel combination of RDS and
what is
R2
RD,
plus R1.
where is RDS in this? I mean, where
Oh,
do you see
RDS is
RDS?
so only only R1 plus R2.
Yeah, there is R1 plus R2, okay. And what sorry, there is this voltage, right? This is, let's say, Vx, or rather V, what do I call it, V in, let's not call that, it's Vx, so this is Vi minus Vx. Okay, so tell me what will it be?
Mayank, like, we shall apply the test voltage.
Let's apply test voltage. Or let's apply test voltage as our friend is suggesting, and let's see what is going to happen because of this test voltage. Okay, I applied a test voltage. Now what? You find out what is the
So
current.
it is it will be
It will pass through, I guess, R1 R1
What is going
current.
to happen because of this? I mean, if you apply V test, what is going to happen? What is going to be the I test? What will this? Okay, tell me what will be the I test?
Current will pass through R1 R1.
Current will pass through R2 R1. Fine. And what else? So first of all, well applying this this thing, what should I do to Vi? Vi should be grounded, right? Am I right?
Yes.
CI will be grounded.
Vi is grounded. Fine. What else? So what will happen? Tell me. Vi is grounded. So what is going to be this voltage here?
Negative. Like AV minus AV times X.
It will be equal to V test.
It will be equal to V test and
V test minus AV time Vx.
minus
AV times Vx.
AV times You're saying this voltage is V test minus AV times Vx.
More like that node voltage.
How is this node voltage? So you can see now this is the problem, right? This is a classic problem. I also talked about this last class. So let's do this. Do you see a problem here? I mean, this is a voltage source, right? This is also a voltage
Like
source, and they are
you're
connected in
shorting the
parallel.
voltage sources.
Yeah, I have shorted two
Like you're
voltage source. What is going to happen?
huge amount of current.
Yeah, this is a catastrophe, right? This is not good. Until unless two voltage sources are equal in magnitude, equal in value, this is a huge catastrophe, isn't it? Huge amount of current will flow. So what should be the output resistance in that condition? For any finite V test, the output resistance, output current I test will be how much? What is huge? Huge in here is, in ideal situation, huge is infinite, okay? So for any finite V test, I test is how much? Infinite. So R out will be how much? V test upon I test. For any finite V test, I test is infinity, right? So what is going to be R out? Some V test
0.
divided by infinite. This will be 0, right? So this this you should have told just like that, right? I mean, in any voltage source, if there is any voltage source, the output resistance of any voltage source is always 0, isn't it? So here also it's a voltage control voltage source only, now it's at the output side, from the output side, this side, it's a voltage, it's a voltage source, right? It's a voltage source at the output side, so the output resistance will be always 0. No doubts there. It doesn't matter whether the gain is infinity or not. So in both these conditions, it will actually be, the output resistance will be 0. Okay.
Means R out must be less than RL.
What? No, you please ask the question again. I couldn't hear it properly. R out must be much less than RL. No, R out is 0, so it will always be less than anything that you connect at the output side. R out is 0, so what is less than 0? This, I mean, R out cannot be a negative quantity, so R out here is less than 0. R out is the minimum.
Like minimum it should be 0. Minimum it should be 0.
It is always 0 here. It's a voltage source here, so it is always 0. Fine. So in an ideal op amp, we know that in an ideal or non-ideal op amp where we implement op amp using a voltage controlled voltage source, the output resistance is always 0. So this block, this particular block, even if it is non-ideal, still it has 0 output resistance, right? This is something which you should remember, because the next problem is going to be, we are going to discuss what happens when this is not equal to 0, when this is not an op amp, when this is not a voltage control voltage source. Let's deal with that. So we already know that, previous question, we already know that AV had to be infinity, right, for this to behave as an ideal op amp, isn't it? We saw that if AV was not equal to infinity, the gain dropped from 6 to 5.66, correct? Guys, are you following me?
Yeah.
Yes.
So if the gain was not, if the op amp gain was not infinity, the overall closed loop gain dropped from 6 to 5.66, right? So first priority is that we need to have infinite gain. That is the first priority, infinite DC gain. Okay, now let's see. So in this case, the op amp VCVS, we do not get it like this, right? As you already know, we have to implement it using some VCCS. Okay, there is some GM and there is some R out. So the first priority which we had earlier, what was the first priority? We need to have infinite DC gain, right? We want to have infinite DC gain, isn't it? So let's assume for time being that this GM, this VCCS, has infinite R out. So what will be the DC gain? GM times R out. DC gain will be what? GM times R out, right? So this will become equal to equal to infinity, the DC gain of this guy.
Can you repeat again, please?
Yeah. So I was saying that we know from our previous question that the first priority which we have from our op amp, this guy, is what? Its gain should be equal to infinity, right? DC
Yes.
gain has to be infinity. Only then will this behave like an ideal op amp. So since we do not have an ideal VCVS, we use a VCCS. Okay, a voltage controlled current source. Now,
Okay.
a voltage controlled current source always has an output resistance, right? We know that there will be an output resistance.
Yes.
So for time being, let's assume that it's an ideal VCCS where the voltage controlled current source, ideal VCCS, has infinite output,
Infinite resistance.
right?
Yeah.
So its DC gain, its DC gain is also infinite, right? It looks like it. It looks
Okay.
like its DC gain is also infinite, right? I mean, there's nothing looks like it. It is actually infinity. The DC gain of this VCCS is actually equal to infinity, correct? Now I will simply replace that VCVS earlier, this AV guy, with this GM cell. Okay, this VCCS. So now solve the questions. So what is going to be V0 if GM tends to infinity? So R out was anyway infinity, GM is also infinity, so what is going to be V0? How do you solve this? So it is very difficult to process infinity in your when you're trying to solve. Okay, so while solving, always solve with finite quantities. Okay, and at the end of the when you get the expression, final expression, then only replace those variables with infinity. Okay, put the limit that those variables are tending to infinity. Only then will you be able to solve it. So tell me, how will you solve here?
Just draw the small signal equivalent and replace outside with the current source
Let's
and
not even do that. Small signal is equivalent. Why do I need to draw them and I know how will it behave, right? So let's. I mean, it's just too much work. You should do that. I mean, you guys should do that. I will not do it here. So I'll just repeat. Simply take this guy here and put it here. This is fine. Okay. Now what? Alright, so now this. Again, like previous question, this guy only has one job, right? It has to supply how much current at the output? GM times whatever difference it sees at the input, right? GM times the voltage difference that it sees at its input. So let's assume that this voltage is Vx, like previous case. So what is going to be the current? This current. What is going to be this current?
GM into VI minus VX.
GM times Vi minus Vx. Okay, good. Huh. Now tell me, now how do I find out Vx? I mean,
VX
I
is
need to somehow eliminate Vx, right? And I out also. What do I do with that? And I know V out is here. So what is going to happen? What will be V0 in terms of I out? Okay, I am writing an equation. Tell me whether it is correct or not. So this is what V0 is. I am saying that V0 is equal to I out times R1 plus R2. Is this correct? Is this correct?
There's an R out also, right? Like that the current should be split between R2, R out and R1,
Which
R2.
R out
Like,
are you talking about?
it was there in the previous diagram.
This
So
one?
if it, right, yeah.
So I assume that R out is infinity, right? I mean, I have also written it here.
There's a difference between GM R out is tending to infinity and R out alone is tending to infinity. So
So there is a
uh,
difference. It will come out. I'll come to that point. But for now, just assume R out is infinity, right? I've assumed R out is infinity, so everything that comes, all the current that comes out here has no other path but R1 and R2, right? The series combination. Am I correct?
yeah,
Yeah.
in
So
that case,
yes. So what is going to be V0 GM times? Correct. This is going to be V0. But now I need to eliminate Vx. So tell me what is going to, what should I do? Again the same thing, right? V0 and Vx has the resistor divider relationship, isn't it? So Vx is equal to V0 times R1 divided by R1 plus R2. So if you put this equation into this guy, what will you get? V0 is equal to Gm times Vi minus V0 times R1 divided by R1 plus R2 into R1 plus R2. What will you get after this, after solving this? So I know that this has already been done in the class, but still you guys are not answering me. So I'm not happy with that. In the lectures, the instructor has already talked about this. So this is how much. Let's split it Gm times Vi times R1 plus R2 minus Gm times V0 times R1. Alright. Good. So this becomes V0 1 plus Gm times R1 equal to Gm times Vi times R1 plus R2. V0 is equal to Gm times R1 plus R2 divided by 1 plus Gm times R1. And times Vi, or rather if I try to write it in other manner, V0 is equal to Gm simply divide Vi over okay, let's do another division. V0 by Vi. I take this guy in out of this. I mean, I simply multiply by R1 plus R2 divided by R1, R1 plus R2 divided by R1 from top and bottom, both top and bottom. So this will be 1 plus, I multiply this guy R1 plus R2 by R1, so 2 times 1 over Gm times R1. Is this correct or something is wrong here?
I think we can do it, Mayank. Basically, you are trying to make GM in the denominator so that it will be 0. 1 by infinity will be 0, and
That's
that
okay.
part
Is the expression correct or not? Or have I done something wrong here?
I
No, expression is correct. Like it's just been inverted here and there, but we have to get the R out, right? Like for R out, we should do that. Like
No,
we have to.
that's fine. I mean,
Do
don't.
test.
I mean, don't go there. First, let me first tell me whether the expression is correct or not. I mean, have I done any mistake in the calculations that I have done so far? Closely observe this. I mean, is there something wrong or not? Because if you say
I think
there's
it is
nothing wrong,
nothing wrong. I
if you
think.
say there's nothing wrong, and if I quickly figure out something is wrong, so it will not be good for you now. Tell me clearly. I mean, observe this closely and tell me whether some. I mean, have I missed anything or not?
Nope.
Nothing is wrong, right?
If we take common Gm from denominator, then it will cancel out, and in denominator it will become 1 upon Gm.
Okay, let me come to that. I am at this place right now. I am at this place right now. So
No, it's correct. Like it's G1 into R1 plus R2 divided by GM1 plus GM R1, which reduces to the previous expression that we have seen, like in the idealized amplifier. So it's correct.
no,
Like
that's fine. If it is not, if it is not, if it is not, I mean, if it is not infinity, so what is the expression? So that is what I'm trying to figure out, whether it is correct or not. Getting my point? Yeah, it looks like it is correct, isn't it? It is actually correct. Nothing is wrong here. So now, yeah, as our friend was saying, that this guy equals how much? Actually, 1 plus R2 upon R1 upon 1 plus 1 over Gm times R1. This is what it is. So yeah, so again, if Gm tends to infinity, so this is the first question, right? If Gm tends to infinity, this guy will tend to So limit gm tending to infinity, v0 by vi is how much? Equal to
1 plus R2 by
1
R1.
plus r2 upon r1. No doubts there. This is fairly easy, correct? But if you can clearly, I mean, what I was trying to impress upon here was this thing, that here the DC gain was infinite anyway, right? Because I assumed R out was infinity, so DC gain was anyway infinite of the op amp. I mean, of this guy, the DC gain was anyway infinite. So why then, in that condition, why did we need another condition that GM also needs to be infinite? I mean, are you guys able to understand my question? In the previous question, the sole condition was that the gain AB should be infinite, right? In the previous question, problem number 1, we wanted, the only condition was AB has to be infinite for this to behave like an ideal op amp and the signal to be amplified to the correct value. And so this becomes equal to 6, right? So this guy is equal to 6, correct?
Yes.
So this for this condition, for this amplification factor, in the previous problem we saw that the only condition required was AB had to be infinity, correct?
Yes.
But in this condition, in this question, in this problem, we see that even when R out is infinity and the DC gain of this op amp becomes infinity, still you can see that V0 by Vi is also a factor of GM times R1, isn't it? So
Yes.
even when GM times R1 was infinity here, still you see that this guy, the overall closed loop gain may not be its ideal value, right? It becomes ideal, it becomes equal to ideal value only when GM also tends to infinity.
Yes.
So what is wrong here? I mean, still the DC gain here is infinity with R out tending to infinity. Still we need another condition, and GM also has to be equal to infinity. So what is wrong here? What is missing here? What is different from the previous case?
I think we are not calculating the GM into R out ever. That is the problem, because whatever current is coming out from that box is going through the R out load resistance.
Okay, so you are thinking in the correct lines, slightly wrong frame. You have framed your argument slightly incorrectly. Okay, the thing is that you see, for that condition to hold true, for the previous problem's condition to hold true, we need an ideal voltage controlled voltage source. Okay, and voltage controlled voltage source has the special characteristic that its output resistance is equal to 0, isn't it? It doesn't matter whatever you have connected at the output, the voltage will not depend upon that, isn't it? The output voltage for an ideal voltage controlled voltage source does not depend upon what you connect at the output, isn't it? However, for ideal voltage controlled current source, the output voltage is a very strong function of what you are going to connect at the output, isn't it? So even when that is why even when this guy individually had infinite gain, the moment you connect something of this kind at the output of this GM, the voltage will no longer be what it was supposed to be in the ideal case, because now this current, the current that is going to come out of this guy is going to flow through where? Through this resistors, right? And then the voltage is, that is why the voltage is very strong function in that case of the output of whatever you connect at the output. However, when GM becomes equal to infinity, okay, when the GM becomes equal to infinity, that is not going to happen anymore. when the GM becomes equal to infinity, it actually tends to the condition that we saw earlier. It tends to a condition, it tends to the same condition as ideal VCVS. Okay, this is what is happening in this particular example. That is why you see that as GM becomes infinity, this tends to the ideal VCVS case. Are you guys able to understand?
Yes.
Think about it. I mean, you will be able to understand. Think about it. Yeah, this is why I have asked this question here, and this is just to understand. So GM, if it is equal to 1 millisiemens, other than instead of infinity, you just need to put the value here, and you will see that it will become less than 6. The value will be less than 6. Yeah. So what is the steady state error when GM is equal to 1 millisiemens?
Yeah, that question I did not understand. What is meaning? What is the meaning of steady state here?
Yeah, steady state is actually this. Generally in this case, it doesn't matter anyway. But steady state in general, it means that when all the steady state is what? Steady state has two meanings. Okay, steady state for DC is what? It means that when there is no change, then there is
Yeah,
everything is, all the
yeah,
voltages are constant. Okay, that is
yeah.
steady state.
Basically, after changing something after a sufficient time, everything is stable. That
Everything
is
is
the
stable,
steady state.
and everything is constant, then it is a steady state for DC signals. Okay, however, when there are when you have when you have some sinusoidal input, or let's say there is no input, but let's say there is some, your system is behaving in some manner which is periodic. Okay, let's say there is some disturbance in the system, and the disturbance is periodic, so then also it will be stable. It is also a steady state. Basically, whatever is happening should always happen in the same manner. So that is the meaning of steady state. Whatever is happening should always happen in the same manner. That is steady state. So in here, the steady state error means what is going to be the final error in the if you apply a signal here and you wait for the transients to die down, okay, for everything to settle, and then find out what your output voltage has settled to compared to what it was supposed to settle to. So that difference will be your steady state error. So is that understood now?
Nope. So are you trying to say if GM is infinity, then what is the steady state? And after GM is that value,
Both
what
conditions
will
are
be the
there.
steady
No,
states?
they are
And
both conditions. So if GM is equal to infinity, so that is the ideal value, right? That is the ideal expected value. Okay.
yes,
So that is what you aspire to achieve. However, in the real circuits, you will not be able to achieve anything which is made using infinite value components, right? So real components have finite values. So you will have some finite value of GM. So with that, definitely you will not achieve the ideal value. You will achieve some value which will be different from ideal value. Correct? So you take the difference between both of them, and that will be your steady state error.
okay.
Getting the point now? So okay, so let's solve this. Okay, it will make more sense. So first tell me what will be the V0 over Vi when this is GM is equal to 1 millisiemens. So 1 plus R2 by R1 is 6, right? And this is how much? 1 plus GM is 1 millisiemens, so 1 over 1 milli times, what is R1? R1 is 20 kilo ohms, na?
Yes.
Yeah. So R1 is 20 kilo ohms. So this K milli go away. 6 plus 6 divided by 1 plus 1 over 20. So how much will this be? Excuse me, 1 second. I have to take a call. Hello. 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 Yes, so how much will this be? 6 divided by 21. So 6 into 20 divided by 21.
Yes, someone already
5.7.
had the answer 5.7.
Oh, that's good. So it will be 5.7. Correct. And how much was it supposed to be? 6. It is only 5.7. So now tell me, uh, yeah, so tell me if Vi is equal to 1 volts, if so this is which question? 4. If Vi equal to 1 volt, then ideal value of V0, this will happen when Gm becomes infinity, right? And this will be how much? 6 volts, correct? So similarly, if Vi is equal to 1 volt and Gm equals to 1 millisiemens, then V0 will be how much? 5.7 volts. So tell me, what is the steady state error? What is the steady state error? 6 volts minus 5.7 volts, 0.3 volts. This is a steady state error. Okay, but we generally when we say error, we generally normalize it, okay, with respect to the ideal value. Why do we do that? When we report error, we generally report fractional error. Why do we do that?
I think we need a reference point, and that is the reference point.
The thing is that you see, if this voltage, if instead of 1 volt this had been 2 volts, what would this be? 12 volts, right? And how much will this be? 5.7 into 2, right? Getting my point? If instead of 1 volt it was 2 volts, and so instead of 6 volt it would have been 6 into 2, 12 volts, right? And instead of instead of 5.7 volts, P0 would have been 5.7 into 2. So what would have been steady state error in that case? Everything multiplied by 2, right? Correct?
Yes.
Yes. So you can clearly see that if the voltage has increased, the doubled rather, so the in that condition the steady state error also doubled. However, so you might get a feeling that your op amp is now behaving even worse than what it was performing earlier. So but that is not the case, right? Your op amp is the same. There is nothing wrong with the op amp. Nothing has changed. It's just that it's only because you have applied a larger input, the error is larger, right? So you need to normalize it with respect to the input. Ideal this thing, you need to normalize it with respect to the ideal that you expect, so that everything is basically normalized to the so that is why you report fractional error. So this is generally, I mean, this concept is very well known, and it is generally taught in 11th class, right? Fractional errors and all those things. Anyways, when you say steady state error, you talk about steady state error, fractional error, right? So this is how it is. This will be 6 volt divided by 5.7 divided by 6 volt. Okay, so how much will this be in that condition? This will be, how much will this be? Correct. And fractional errors are dimensionless, okay, because you divide it by the same dimensional value. So this is 0.05 magnitude, okay. There is no unit I mean involved with this. So in terms of percentage, how much is this? Zero point zero five into 100, right? 5.
Yes.
So if it is even not mentioned in the question, we have to calculate the steady state error in fractional error.
Generally, that is how it is assumed. I mean, fractional error is something which we generally seek for. Okay, it is a fractional error which we report generally. It's just, I mean, it doesn't make sense to report the absolute error because it just doesn't make sense. It changes simply
Okay.
because of the input.
Thank you.
Yeah. So I think that is clear now. There is no question. Okay. This question is not that difficult after. I mean, actually. So basically, in this question, you have two MOSFETs. Okay, this is basically a differential amplifier. Okay, it looks like a differential amplifier. You have two MOSFETs which have the same W by L, which has the same and both have the same threshold voltage and mu and Cox value. Okay, and now you have applied the same common mode voltage at both places. Okay, so tell me what is going to be the current I1 and I2. I mean, is there any relationship between both of these, I1 and I2?
Yeah, there's some I bias. So yeah.
Yeah, it will, some will be I bias, correct, but then again, what will be I1 and I2? I mean, I do not want you to calculate, but you can clearly, you can
So
say
4
They are
milliamp,
equal.
2 milliamp to milliamp.
yeah, exactly, both will be equal to each other, isn't it? And why will that be? I mean, even when R1 and R2 are not same, you can see that R1 and R2 are not same here, right?
Because the bias voltage is the same.
Correct. Because the bias voltages are same, right? Because VGS for both of them are same. And in this question, okay, I have not written it explicitly, but you have to neglect channel modulation. Okay. So once you neglect channel modulation, there is nothing else on which the current will depend upon. Okay, the current only depends upon VGS in this condition, which is the same for both of these transistors. So it doesn't matter what you connect at the drain of these transistors, the current will always be same for both of these. So I1 and I2 both will be 2 milliampere each, correct? So yeah, so this will be how much? 2 milliamps and 2 milliamps. Fine. So what will be GM1 and GM2? You have to calculate that, okay? This you have to calculate. So you know the current that is going to flow through this MOSFET. So you can find out what is the VGS, right?
Yeah, they will also be the same because the current.
Yeah, they will be same. I'm not denying that. I'm trying to find out. I'm trying to ask you, what will be the value? How will you find out? You find out the values. GM1 is what?
Yeah, the square root of 2 mu PCOX into IDS. That formula.
Yes,
Right?
correct. So GM1 is equal to GM2. This is problem number 2. Okay, and question part 2. So this will be equal to square root of 2 times ID times mu n Cox W over L. So what will be ID here? What will be ID here?
2 milliamp.
2 milliamp, exactly. It will not be 4 milliamp. So people make that mistake sometimes. And mu and Cox is how much? 0.1, right? milli. What is W by L? So this is
20.
20. So how much will this be? So milli come out of square root as milli only, right? So let's take that. 2 into 2 will be 4. 4 into 2 is 8. So it will be root over 8 millisiemens, right? 2 root 2 millisiemens. So forgive me for this weird number. I just framed the question just like that. I didn't care about the values. So 2 root 2 millisiemens. Fine. So GM1, GM2 is also set. I mean, you know how much it is. Now find the value of Vx. Yeah,
There is a question I have.
tell me.
So let's say you know the VCM. Okay, so let's say you know that value, and you calculated the voltage gate to source is something, let's say 3 volt.
Okay.
Okay. So your Vx will be VCM minus that value.
Yes.
Right. But my question is, from where that Vx is coming?
I didn't get your question.
Yeah, so that's my problem also.
No, I didn't understand your question at all. Vx is coming. I mean, there is some node. It will have some voltage, right? I mean,
yeah, it will have some voltage. Yes.
So any node anywhere will have some voltage.
So it is just because of that MOSFET the Vx is coming, right?
Again, I understand. I don't understand. Vx can be anything. If the I bias thing was not here, then Vx. I mean, sorry. Let's say if I bias is not there, and Vx is, and this node is directly connected to ground, what will be Vx in that condition?
We have to get the VGS for that corresponding ID because it's 1 to 1 in saturation region.
That's okay.
Then yeah.
Vx will be how much?
It will be 0. Zero if grounded.
Right? Still, there is some Vx now. I mean, it's just that Vx is 0 in this case because you have explicitly grounded it. So in this case, we have not explicitly grounded it. We have connected it to some I bias. Okay. So there will be some voltage here. That's all. Vx will be some voltage, and that voltage will be because this Vx acts because Vx is what? It's a source node for both M1 and M2, right? So the VGS will be what for both M1 and M2 will be as you already said VGS is what? VCM minus Vx, that is VGS.
Yes.
Yeah. So I don't know whether this answers your question or not, but I do not understand the question at all. I mean, I don't know what.
No. Okay. My understanding of any voltage, I may sound stupid again. So my concept is if current through some resistance, then the voltage difference will generate, right? So here the MOSFET M1 is there is a current through MOSFET M1, and that is somehow some part of it passing through the Vx.
That is not
so there should be a resistance then there
so that's what
to generate the Vx.
This is a current source. Okay, current source across the current is flowing actually across the current source, isn't it? So there's something here. There is some component here. You cannot. Are you able to listen to me? Hear me?
No, your voice was.
Okay, fine. So what I was saying is, you can see that here also between Vx and ground, there is some thing which is connected, isn't it? There is a current source which is connected here.
Yes.
Yeah. So current source is just that a current source. The voltage across the current source cannot be set. I mean, you cannot say anything about it. Just looking at it, it depends upon how the other things are behaving. So voltage across the current source can be anything. But to answer your question, there is something which is connected. It's just that it's a current source.
Okay, understood.
Yeah. Fine. So yeah. So as our friend just told, how to find out Vx, right? You just need to find out what is the VGS here. So VGS can be found out. How can you find out VGS? We know the
The
current.
formula.
We know the current. We know the WYL and everything. So VGS can be easily be found. So from there you find out what is Vx. Okay. And then, yeah, so this you have to do yourself, because this was covered in lectures. So I would like to, and even if it is not covered in lectures, you should use your learning till now how to find out the incremental gain. You know how to find out incremental gain, right? Just apply an input, and other than the input that you are applying, just ground all the other inputs, and any DC bias will be 0. So use that knowledge of yours which you have gained starting from the starting of the course to find out incremental gain, and just use this and find out, because I'm not going to solve this.
Yeah, so I have a question.
Huh.
So there is a in lecture you can find a formula for Vx,
Okay.
right?
Mm.
And that is the incremental voltage depending on the gate voltage.
Okay.
So you uh, short all the DC values and only just incremental value, and you can have the Vx.
Hmm.
There is a formula GM1 V1 plus GM2 V2 and all.
Hmm.
So that is the straightforward, or we have to calculate.
You use your I mean, you use your logic, whatever you think is correct, so you should use that. And I'm not going to answer that right now. You think about it. So is that
Okay.
correct, or you need to do something else? Okay, that might be correct. I'm just not saying anything here. And yeah, so find out us. Okay, this is, these two questions I will answer in the next session. Okay, these two questions, sorry, I would like you to think about these two questions yourself. Okay. Oh, this question is not actually that great. So this question you can solve right now here only. So what is going to happen as R1 increases? First of all, as our friend asked in the very first I mean, in the first few minutes, our friend asked how do you find out swing limits and all. So here also there's a question on what is the maximum value of R1 for all transistors to remain in saturation. So anytime you get a question where you have to find out conditions on certain parameters to ensure saturation for all transistors, you have to first ask the question, what happens if that condition is violated, or why does that condition arise in the first place. So here also the question is, what is the maximum value of R1 for all transistors to remain in saturation. So in your brain you should ask the following question, that okay, what happens if I increase the value of R1? What is going to happen if I increase the value of R1? Okay, first of all you should ask yourself the question that what is going to happen if I increase the value of R1? Why has this question come at the first place? So that is the first question that you should ask yourself. Then you will be able to answer any question which is swing related or constraint related. So tell me, what is going to happen if R1 or R2 increase?
Yeah, the VDS is going to drop across M1 or M2.
Yeah, because the current is same, right? Current is not going to change. Current is being set by the gate to source voltage, which is always same. Oh no, rather current is not going being set by that also. Current is being set by this current source, right? This current source sets the current, right? The current is 2 milliampere in both the branches, which is not going to change. So if you start increasing R1, and that is why, since R2 is also related to R1, so R2 will also increase, right? So if you start increasing R1, what is going to happen? Both of these resistances are going to increase, and the corresponding VDS value is going to decrease, right? Because the resistance drop across this is going to increase. So there will come a time when this VDS will become such that this transistor goes out of saturation. So this is fairly easy question. I'm not going to solve this here. I just want to discuss the idea. So I think this is what I want to discuss today. This question I will discuss in the next session. This question I will discuss in the next session. Okay. Interesting thing here. All right, so I would like you try. I'd like you to try this anyway. Think about it. Just try to. I mean, don't solve anything. Don't solve equation at all. Just try to think qualitatively what is going to happen. Okay, what you should expect here. All right, so I think we'll just conclude the session here itself. I'll again we'll again meet on next Tuesday.
Yeah, just a small question.
Yes.
So I1 plus small I1 is called the transient current.
I mean, total current is basically total current.
Okay,
current
so total
is-
current is called the transient current.
no, I just written it like this here. Transient
Okay.
current means so there is bias current, right? Since I already
Yes.
denoted bias current with I1 and I2, how will I denote the total current here? So instead of
Okay,
that,
okay,
total,
okay.
I should write here total current. So just write total current.
No, I'm just asking if you give this question in the exam, then we should understand now what
The
to
transient
calculate.
current is just that there is a transient, right? There's a transient voltage here, right? Transient means something which is changing with time. That's all. So this is a transient voltage, right? Because of this, there will be a current which will also change with time. So that is why I wrote it transient current. But anyway,
Okay,
don't
thank
confuse
you.
with that. What is the total current? That's all. Anyway, so I think we'll just conclude it here.
Yeah, just one second. Would you have a couple of 5-10 minutes for some more conceptual questions? I had some doubts regarding. Professor has discussed many examples like with drain gate current, drain gate biasing, and the connection of like voltage buffers at the output in various circuits. So could you please take an example? And he has, and on the while he has made certain approximations. Some transistors he has just said that okay, you are looking into the source, so it is 1 by G1 GM, and like some flavor on some insight on how to when to take a transistor as only a resistor and when to sort of use like actually put in the entire small signal
No, that actually that is that actually
in an
comes.
exam when the
Yeah, one second. So let me tell you.
yeah.
So that comes with practice, okay? So in general, you should draw small signal analysis, small signal model for everything. Okay, that is how you should learn at from starting. Once you start
Okay.
seeing, once you learn that, you'll start seeing that certain kind of configurations always result in certain kind of basically if it is a common gate situation, then from one side it will look like it is a 1 over GM kind of resistance, okay, and from other side it will look like it is very high resistance. So it becomes kind of uh, when once you start doing that, after a while you will start seeing that okay, it is actually it can be replaced with a resistor, and also it comes with practice, okay. I'll try
Yeah.
to summarize those things in the last session, okay. That is the last
Okay.
12th week.
Okay.
Try to
Because
summarize this thing.
we have to examine like just another 2 or 3 weeks only, and like I what I believe is that some at least some of the questions will be of like some slightly complex character,
It doesn't
and
matter. It doesn't matter. See, when I learnt also, the learning should be in this way also. Only that you should do the small signal model. It's a good thing. You should do small signal model as much as you can, because if you do that now, you'll not have to do that ever again. Okay, so do the
okay,
small signal modeling and then you solve it. It's a good practice. Okay.
okay,
So I
yeah,
will anyway try to summarize this thing. So please remind me again, okay, on 12 on the last week. So today is 10th,
yeah,
right? So two more
yeah,
weeks. So next to next week,
okay,
please remind me this thing that you wanted to uh, basically see how things are. Just remind
yeah,
me the
yeah.
same thing which you just talked about right now. I will
Yeah,
explain this.
sorry for this extra question. Also, like I had, even in the discussion group, I had asked for some lab exercises and all those things. Like because like if I try like I looked at that LT spice and all those things, and
Uh-huh.
there are so many dizzying array of transistors and how to come up with like some non-contradictory specifications and all. Like if you've got from your own courses, if you've got some lab exercises or okay, design this differential
That's what I
amplifier.
mean. Once you learn, so
Yeah.
diff amp is something which you need to learn at least. So that's why I said differential amplifier. Once you finish this, so at the
Yeah.
end of the course, I will post it in the discussion forum. Okay, a question like that. Try to solve
Yeah.
it on
Yeah, like around 5 or 6 like sort of sample designs, so that we'll just keep
one will be
wandering.
enough.
I wanted a lot, so like
One will be enough. One will be enough.
yeah.
Do it diligently. One will be enough.
Okay. Thank you very much.
Okay. All right, guys. Thank you. Thank you for joining. We'll meet again next Tuesday.
Thank you.
Thank you.